Modern artificial intelligence runs on massive terrestrial data centers. Training and operating large language models requires tens of thousands of specialized GPUs, and running them continuously demands a staggering amount of local electricity and millions of gallons of fresh water just to keep the hardware from overheating. This animated graph illustrates the problem. By 2035, global AI electricity demand is projected to hit 1,700 terawatt-hours. This red curve represents that exponential growth, completely eclipsing the flat line below it, which shows our current strained electrical grid capacity. Building enough power plants to meet this continuous load on Earth is physically and economically unfeasible. Faced with this hard physical limit, SpaceX have proposed a radically different architecture. Instead of trying to force terrestrial grids to accommodate AI, they want to move the infrastructure off the planet entirely. In a recent FCC filing, SpaceX requested authorization to launch a massive orbital data center system. They intend to deploy up to 1 million AI-equipped satellites into low Earth orbit, where they can bypass terrestrial power grids and run on constant solar energy. Going to space solves the power generation equation immediately. But the moment you move a high-performance computer into orbit, you trade an energy problem for a thermodynamics problem. The hardware SpaceX is designing for these satellites is incredibly dense. Each unit is expected to house the equivalent of a server rack, pulling up to 150 kilowatts of peak power to run enterprise-grade chips like Nvidia's latest GPUs. Down on Earth, a machine running that hot survives through convection. Air or liquid coolant absorbs the thermal energy from the processors and carries it away into the surrounding atmosphere. Heat naturally transfers from hot, dense objects to the cold air around them. But space is a vacuum. Without atmospheric molecules to conduct or convect the heat away, this thermal energy has nowhere to go. If you turn on a server rack like this in orbit without a way to dump the heat, the processors will rapidly cook themselves to death in their own waste energy. Securing unlimited solar power is only half the equation. For this orbital constellation to function, the real battle is managing the relentless buildup of heat. To survive, SpaceX plans to equip each satellite with deployable liquid radiators spanning 110 square meters. As noted in their FCC application, the system relies strictly on radiative heat dissipation. Instead of transferring heat to air, the liquid absorbs the computer's heat and radiates it out as infrared light into the deep cold of space. You cannot run ordinary water through these massive external panels. In an unpressurized vacuum and extreme temperature swings, water is unpredictable. It will either boil off instantly or freeze solid inside the pipes, destroying the cooling loop. The most viable alternative for this extreme environment is ammonia. It remains liquid down to incredibly low temperatures, effectively transporting heat to large exterior panels. It's the exact same chemical system the International Space Station uses to keep its own hardware from melting. But pumping massive volumes of ammonia through a 110 square meter radiator adds immense mechanical complexity. These active fluid loops require pumps, valves, and redundant pressure systems, all operating continuously. A single micrometeorite strike or mechanical failure in the pump means the satellite instantly loses its ability to cool down. To dissipate 150 kilowatts of heat, SpaceX has to rely on complex, pressurized pipes full of toxic chemicals. The physics of heat transfer forces the satellite to depend on a highly vulnerable mechanical loop. Those massive radiator panels introduce a secondary complication. At low Earth orbit altitudes between 500 and 2,000 kilometers, the atmosphere is thin but still present. A 110 square meter panel acts like a giant sail, catching trace atmospheric particles and creating intense drag. To prevent the satellite from rapidly losing altitude and burning up, it must apply constant thrust. Traditional ion thrusters do the job, but they require heavy onboard propellant. When that limited propellant runs out, the satellite dies. Proposed a highly unconventional solution to solve both the heat and drag problems at the exact same time. It's a concept known as thermal photonic propulsion. Here's how it works. Instead of radiating heat uniformly, the liquid ammonia is routed asymmetrically through the dual-sided cooling panels. This forces the intense infrared heat from the GPUs to radiate out into space only from one specific side of the panel. Because photons actually carry momentum, firing all that infrared light in a single direction produces a tiny reactive physical force. The heat radiation itself acts as a continuous microthruster, generating just enough push to counteract the atmospheric drag on the panels. The satellite uses its own waste heat as limitless fuel for station keeping. By turning the cooling system directly into the engine, this architecture bypasses traditional propellant limits entirely. An asymmetrical photon thruster powered by waste heat is an elegant piece of physics. But when you scale that single theoretical design up to a proposed constellation of 1 million operational units, the mathematics of failure becomes severe. Even with an incredibly high 99% operational success rate, a million satellite network means 10,000 units will experience mechanical or thermal failure. That leaves 10,000 dead, uncontrollable data centers drifting in orbit. As these failed satellites lose altitude and incinerate, tons of vaporized heavy metals, shattered GPU components, and hundreds of gallons of ammonia directly into the atmosphere. Relocating AI to orbit bypasses the terrestrial grid, but it forces a permanent reliance on fragile, high-pressure cooling loops. The feasibility of the entire network depends on a thermal management strategy that leaves no margin for mechanical error.